I'm recording and I have audio. All right. Set that going around the room, please. So who has questions for homework? Cool. Do you have a question and you just don't want to go first? Oh. Okay. Well, everybody here was in lab yesterday, right? Yeah. Okay. Then this is going to be, actually this will be more kind of a review for you. We need to cover sections 3.1, 2, 3.2, 3.3, and 3.4 today. So you'll be ready to do your homework. And this is just covering vectors. Thank you. Just covering over what we did in vectors. So let's revisit vectors and give you all a chance to ask any questions or get any clarifications that you still haven't quite worked out. There are two quantities, two things that we're going to be dealing with: vectors and scalars. Okay? A scalar is a magnitude only. A vector is a magnitude and a direction. And in point of fact, if you multiply a vector by a scalar, you change the magnitude by that much. So a scalar is called a scalar because it scales the vector. Scales it up or down, depending on whether it's greater or less than 1. But it changes the magnitude of the vector. Now, adding vectors together. There are different ways of looking at this, but what I want you to do is I want you to visually understand what you're doing when you add vectors together. So let's take a couple of random vectors. The characteristics of the vector that matter, that are quantified, are the magnitude, which when you're drawing a vector is represented by the length of the vector, and then the direction, which when they're drawn like so, call it M1, makes that M2, theta 1 and theta 2. So when you're drawing vectors, what matters is how big they are, how long they are, their magnitude, and their direction. When you're adding these two vectors together, the way to visualize it is by putting tip to tail. If you're going to add this one to this one, you start by drawing the first one, and then you draw the second one beginning at the tip of the first one. There's M1 and M2. Then the resultant vector, the sum, or what we call the vector sum of these two vectors, is the vector that results when you draw a new vector from the tail of the first vector to the tip of the second. Which becomes a new vector and a new direction. You were in lab yesterday, you've done this. In fact, this was the first vector we did. You drew two vectors, 1, 2, and then you redrew the second vector from the tip of the first vector in order to complete the graphical addition of the two vectors. That worked. In that case, we were using right perpendicular vectors, but in fact, the vectors do not have to be perpendicular. You can have two vectors. Morning, Nick. You can have two vectors at any arbitrary angle and add them together the same way. Another way of looking at it is to, say, complete the parallelogram. If you look at these two vectors as two sides of a parallelogram, you can complete the parallelogram here. And that will give you the resultant vector. Let's look at why that is, because we're going to learn a little something about adding vectors. If we were going to do this the way we did it yesterday, we would be taking and redrawing this vector here to get that sum. But now, here's the question. Does it matter which order you add vectors in? If this is V1 and this is V2, is V1 plus V2 the same as V2 plus V1? And the answer is yes, it absolutely is. It doesn't matter which order you add vectors in. They will add to the same. And you can see that here by completing the parallelogram. We added this vector to V1 to V2 by redrawing V1 here from the tip of V2 up. We could just as easily have drawn vector V2 onto vector V1. In both cases, we would have ended up with the same third vector. So it didn't matter which one we added to the other. When we added the two together, we got the same vector sum. Now, this is something that gave a couple of people yesterday trouble. When we started adding vectors, when you complete the parallelogram, basically doing the same tip-to-tail geometric trick, but you don't have to redraw the vector. You just complete the parallelogram, and then you draw your resultant vector to the opposite corner from the common tails. This is where a couple of people yesterday messed up, because once they did this, they tried to draw the resultant vector from tip to tip. That is wrong. You need to draw, if you're going to complete the parallelogram, you need to draw from the common tail, position of both tails, to the opposite corner of the parallelogram. What you are effectively doing, like I just showed, is you're either adding this vector to this one, like going tip to tail here, or you're adding this vector to this one by going tip to tail here. And since it doesn't matter which order you add the vectors in, you're going to end up at this same far corner point. Okay? Now, does anyone have any questions about that? And for those of you who've just joined us, A, make sure you get signed in, and B, do you have any homework questions? Nope, none? All right. Now, Let's talk about polar versus rectangular. Again, this is another point of confusion for several people yesterday. When you convert between polar and rectangular form, you are only changing the way that... Did she sign? Did you sign? Okay, thank you. All you're changing is the way you describe the vector. You're not changing the vector in any way at all. Whether you describe it as a polar form vector with a magnitude and a direction, or in rectangular form as the vector sum of right angle vectors, you're describing the same vector. So let's review that and look at how you convert from polar into rectangular. Because once you understand how to add vectors and what's actually happening when you add vectors, rectangular form becomes very intuitive. In polar form, you describe a vector as a magnitude, which when we draw it is proportional to the length of the vector, and a direction. We'll call this magnitude 1 and theta 1, angle 1. Now, if you draw this vector on the Cartesian plane, or the rectangular coordinate plane of the x and y axes, you can see just by looking that this vector is the completion of that parallelogram, which in this case, since everything's orthogonal, is a right angle or rectangular parallelogram, which makes it a rectangular coordinate system. We calculate the projection of this vector onto the x-axis, which gives us the component v sub x, and its projection onto the y-axis, which gives us v sub y. You could say that we are decomposing the vector v into its orthogonal components, v sub x and v sub y. Now, in order to write this as a vector, we define two unit vectors that are 1 unit length, 1 unit long. The one along the x-axis we define as the unit vector I, which is denoted as a lowercase I with a caret over it. And we define the vertical or the y-axis unit vector as j, which is a lowercase j with a caret over it. Now, what happens to any vector when you multiply it by a scalar? Anybody? Thank you. The magnitude changes, absolutely. It can get longer or it can get shorter. If you multiply a vector by a scalar greater than 1, it will get bigger. The magnitude will increase. If you multiply a vector by a scalar that's less than 1, its magnitude will decrease. but the scalar will scale the vector. So if we, now this, you'll notice I drew this Vx component not as a vector, but as a magnitude, as just a length. When we multiply this length, V sub x, by the unit vector I, we create a horizontal vector along the x-axis that is V sub x long. Okay, we have this unit vector I, we make it that long, which we write as V sub x times the unit vector I, the scalar times the vector. We do the same thing in the vertical axis, where we multiply the unit vector j by V sub y, and in doing so create a vertical vector V sub y. That is the length V sub y scaling the unit vector j. So, when we write it this way, we are now saying that the vector v is the vector sum of this vector, the magnitude v sub x at 0 degrees, pointing along the x-axis, plus the vector that is v sub y in magnitude, pointing straight up at 90 degrees. We could write both of these components and in polar form as v sub x at an angle of 0 degrees plus v sub y at an angle of 90 degrees. Okay. This and this both describe the same vector. This and this both describe the same vector. This vector, which is here, is the vector sum of those two vectors. So, we can also write it as v at an angle theta. This is one description of that vector. This is another description of the same vector. Okay, it's not two different vectors. Okay? So, when you have a vector in polar coordinates, you will have a magnitude and an angle. When you have a vector in rectangular coordinates, you will have two magnitudes that are understood to be perpendicular. Okay? Now let's talk again about, let's continue looking at this as a vector sum, and let's talk about the details of how this becomes that. We've already said you can add any two vectors graphically, or you can visualize it graphically when you draw the two vectors and in this case Earlier, we just drew any arbitrary two vectors, and we got a parallelogram. To complete the resultant vector. We can do the same thing here. We complete the parallelogram. And we get our resultant vector. All right? So everyone sees how this is going on. At theta, well, from trigonometry, we know that V, the magnitude of V, if we divide the opposite side of a right triangle by the hypotenuse of that triangle, that will give us the cosine of that angle. And if we divide that was the adjacent, this is the opposite side. If we divide the opposite side of a right triangle by its hypotenuse, that will give us the sine of that angle. From this, we can multiply both sides by the magnitude V, and we get the length V sub x is equal to the magnitude of V times the cosine of theta. And similarly, we get V sub y is the magnitude of V times the sine of the angle theta. And this is how we break down a polar representation of a vector into its rectangular components. These are lengths. Okay? I want to emphasize this. Right now, the way I've got this written, V sub x and V sub y are not vectors. They are lengths. They're just magnitudes. They become vectors when we multiply them and use them to scale the unit vectors I and j. Okay, so strictly speaking, the vector V is not equal to V sub x plus V sub y. Because V sub x plus V sub y is just a sum of scalars. V is equal to V sub x times the vector I plus V sub y times the vector j. So in that regard, it's very much like making sure your units match. A vector cannot be the sum of two scalars. A vector must be the sum of two vectors. So it really is important to keep straight when you're dealing with vectors and when you're dealing with scalars. Now, as I pointed out to you yesterday, I'm going to clean up some space here. Everybody got notes? Any notes they want copied down? All right, let me clean up some space. So now we're not going to be doing it in this class, but if you were in another class where you were needing to do such things, in order to multiply vectors, you would need them in polar form. Okay? This is actually why we're not going to get into it in this class, because when you start multiplying vectors, then you have to worry about whether you're talking about a dot product or a cross product. They're not the same. But in general, if you wanted to multiply V1 times V2, then you would write the magnitude of V1 times the magnitude of V2. Okay? And V1 at theta 1 times V2 at theta 2, you would then add the angles. Okay? Of course, if you were dividing them, then you would divide V1 by V2 at the angle of theta 1 minus theta 2. Okay? This is generally a very limited and special case of two-dimensional vectors, so don't worry about writing this down or memorizing it, because if you ever get to where you are going to be multiplying vectors, then you're going to need to know dot products versus cross products, which gets into matrix math, and we're not going to go into that. So I just wanted to point out to you that if you're multiplying, you want your vectors in polar form. And if you're dividing, what's division except multiplication by a reciprocal? All right. That is all we're going to say about this here. We went to a whole lot of trouble to learn how to convert these polar coordinate vectors into rectangular coordinates, because when you add vectors, you have to put them in rectangular form. You cannot add them directly in polar form. Now let's look at why that is. Here is vector 1. And let's say that is vector 2. How do you add them? Well, you can go tip to tail, like so, and that gives you this resultant vector. Okay. You could also do the completion of the parallelogram. But let's look at what's actually happening here. If we convert this one into rectangular coordinates, we've got V1 sub x and V1 sub y. Here and here. Here we've got V2 sub x and V2 sub y. So, here we put V1 sub x, and then we add to that V2 sub x, that brings us to the horizontal end of our original vector. Now we take V1 sub y and add to it V2 sub y. And that brings us to our resultant vertical component. So, once we've converted our vectors into rectangular coordinates, we can get the resultant vector sum by simply adding the associated components. Add the x components, magnitudes together, and multiply by I. Add the vertical components together, the y components together, and multiply by j. And you get your resultant vector. Now, that's adding vectors. What about subtracting vectors? Just like multiplication is simply, division is simply multiplication by the reciprocal. Subtraction is simply the addition of a negative. That's all it is. What is negative 1? It's a scalar. So if you want to, what happens when you multiply a vector by a scalar? In this case, you change its direction. If you multiply it by 1, the magnitude 1 doesn't change the magnitude of the vector at all. But the negative sign changes the direction of it. Let's look at the example here. We've got our vector v, we said 2, so I'll call it v2. Here it is. v2xi and v2yj. Those are the two components. What happens when we multiply by negative 1? Minus v2xi minus v2yj. And now their vector sum is the same vector we started with, but pointing 180 degrees in the opposite direction. Strictly speaking, and I'm not advocating this, okay, don't look for this rule in the book, but if you were going to multiply in polar form, you'd be saying minus 1 times v2 at an angle of theta. That would be, now intuitively you would think, well, that would be minus v2 at an angle of theta. But that's, and you could write it that way, because if this is theta and this is plus v2, if you go minus v2 at that same angle along that same line, you're going in the opposite direction. But strictly speaking, what this would actually become is v2, because how do you have a negative, how do you have a, never mind, v2 at an angle of theta plus 180 degrees, or theta minus 180 degrees. Okay. As you can see, that would become very convoluted very quickly. When you put everything in rectangular coordinates, you can add the components. If you multiply one of the vectors by a negative sign, you get the negative of that vector. Now what happens when you add, if that's v1 and that's v2, what happens when you add them? You get v1 plus v2. What if you subtract them? What's the negative of this? You get a very different result. There's no Does anyone have any questions about this so far? What about from the from the lab yesterday? Okay, well then, I'm going to give you all a couple of, go over a couple of the examples, or at least the kinds of examples that they cover in the book. You're going to see this in the homework, I'm pretty sure, if I remember correctly. If you're adding this vector plus this vector plus that vector, how do you add all three of them together? Well, no, you add them as they are. You would draw the first one graphically, you would draw the first one, then you would draw the second one, and you would draw the third one. And your resultant vector would go to right there. And notice that that's the same as adding all of the horizontal components and all of the vertical components. Does everyone see how that worked? I mean, visually, do you see what's happening when you break it down into its rectangular components and then just add them together? It can get, they make some of these kind of convoluted, but if you just work them out one piece at a time, you'll get the right answers. I really can't believe no one had any questions today. What about from the exam? Well, unless someone has a question, then I'm going to go ahead and start looking at where we're going next week. Section 3.5 with projectile motion, because that's the whole point of chapter 3, is we're going to be dealing with motion in 2 dimensions instead of just 1. I take it everyone still has all of their kinematic equations, right? Okay. This is sort of the beauty of describing things with vectors, is it allows you to treat complex solutions much in a much simplified way. What is, we haven't really covered the laws of motion yet, but I'm sure you've all heard that a body in motion tends to stay in motion unless acted upon by an outside force. And a body at rest will stay at rest unless acted upon by an outside force. Well, it turns out that when we start dealing with motion in 2 dimensions, we can treat both axes of motion, the horizontal and the vertical, independently of each other. If a car goes over a cliff, and at the moment it leaves that cliff, its horizontal velocity is v sub x, horizontally. Once it leaves that cliff, and if we ignore air resistance, the drag of the atmosphere as it travels through the air, what force will be acting upon that vehicle? Now, if it were still on the ground, it could be accelerating by transferring energy from the wheels to the ground and making it go faster, or if it had any sense, it could be slamming on the brakes and trying to slow down before it got to the cliff. Once it leaves the surface of the ground, if we're neglecting air resistance and drag, there's nothing to either speed it up or slow it down horizontally. So its velocity will then remain constant. Or its horizontal velocity, I should say, will not change. It will continue. And I just went through that one too long. As long as it, forever, nothing, until something acts to slow it down in that horizontal axis, its horizontal velocity will stay the same. Now here's the problem, and if you've ever seen Thelma and Louise, you're very well familiar with this problem. While it's on the ground, there is another force acting upon it. Gravity is pulling it down, accelerating it at 9.8 meters per second squared. So it has a vertical force pushing down on it. It's just that while it's on the ground is pushing back up with the same equal and opposite force. Once it leaves the ground, that's no longer the case. And now it's going to start accelerating vertically at the same time at 9.8 meters per second per second. So here, it accelerates down with that velocity, with that much. See what's happening? Now eventually it'll be falling so fast that you can no longer neglect air resistance. Has anyone here ever heard of terminal velocity? Can you describe terminal velocity? It's the fastest a given body can fall through the atmosphere. What happens is, and if I used to skydive, so what happens is you jump out of the plane, you start falling. Well, you can only ignore air drag for so long before it becomes significant, and then at some point, the drag of the air pushing up is going to equal the force of gravity pushing down. And once those two forces are equal and opposite, you stop accelerating. That doesn't mean you stop falling. It means that from then on, you fall at a constant speed. You don't accelerate anymore. Eventually, the ground will stop you if the parachute doesn't. But this is what happens here. And like I said, at some point, the ground will stop the car. In the case of Thelma and Louise, it was the bottom of the Grand Canyon. It was the Grand Canyon, right? Who saw the movie? It was Grand Canyon? Yeah. Believe it or not, I've never actually seen the whole movie. I've seen pieces of it. Kind of like that movie, The Princess Bride. It's bizarre because it's one of my favorite movies. And I don't think there's any part of it I've never seen, but I've never once seen the whole thing from beginning to end. What we're going to learn next week is that we can analyze this motion using the same kinematic equations that we use for motion in one dimension. But what we will have to do is ask, how far in the x direction will this car travel before it comes to a stop? Well, whatever speed it's moving at horizontally, it's going to continue to move at that speed horizontally until the ground stops. So what you will have to then do is analyze, how long will it take this vehicle once it leaves this cliff? How long will it take it to fall to the ground? How fast will it be going when it hits the ground? You can analyze that independently of any horizontal motion that it's going to undergo, any horizontal translation it's going to undergo while it falls. Once you determine how long that takes, then you can multiply the horizontal velocity by that much time, and you will find out how far it will have traveled in the horizontal when it hits the ground. See how that'll work? Well, y'all are one active group of students. It's like I'm keeping y'all up or something. It's a brand new day. You know that as of today, at the end of today, this semester is 1/3 of the way over. This is the end of week 5 out of 15. So, how many of you feel like you know any more physics than you started with? Yeah, thanks. I appreciate it. Little pity hand raising. Gotcha. Well, for all the times I've gone over and kept you from getting to your next class, I'm going to let you out early today. If you have any questions on the homework, you know where my office is. You've got my email address. And, hey, you. Why did it do that? It has flat gone nuts. Back here, you.